Hello everyone, my name is Yunchao Liu and I'm from the Vanderbilt University. Today I'm happy to share a new graph neural network framework we designed for the drug discovery campaign. Let's first start with something we are all familiar with, SARS-CoV-2, aka the coronavirus. Recently, Pfizer has announced that they found a small molecule that can cure the disease. This small molecule can bind and inhibit the function of a target protein, and this target protein is essential for the viral replication. So by binding and inhibiting the function of this target protein, this small molecule essentially cures the disease. So in a similar fashion, for a certain disease, scientists will first try to identify some target that is related to the disease, and then scientists will try to find a small molecule that can bind and alter the function of this target. So by altering the function of the target, essentially this small molecule helps cure the disease. Then the question is how to find this small molecule. Traditionally, scientists will use some automated equipment like this high-throughput screening equipment to screen through a large chemical libraries. However, this process is very expensive, and also the hit rate of finding promising molecules is really low, usually estimated to be less than 1%. So one way of improving this process is to use experimental data to train a graph neural network, or GNN. And then we can use the trained graph neural network to screen a much larger virtual libraries and prioritize those predicted active molecules for further experimental validation. So here I will give some background for the graph neural network. Most graph neural networks employ this neural message passing framework. Essentially, for a focal node and its neighbor, a message is made from the focal node and its neighbor. Then those messages will be aggregated and the new node state will be updated based on this aggregated message. So the key idea here is to generate new node embedding by aggregating attributes of the neighboring nodes. However, we can see that there is a limitation for this graph neural network. Graph neural network cannot distinguish different ordering of neighbors. However, this ordering is important. For example, in chemistry, we have chiral molecules, which are essentially the mirror image of each other, and the chirality plays a significant role in binding. So we want to capture these neighbor ordering. So here we design the molecular convolution to solve this problem. To talk about molecular convolution, let's first look at image convolution in this edge detection example. So here is an image, and if we look at a specific image patch and convolve this with a vertical kernel, and we can get a convoluted value. We can also convolve this with a horizontal kernel and get another value. And from this example, we can make several observations. First of all, the higher the convoluted value, the more similar a patch is to the kernel. And secondly, we can notice that the patterns in the kernel also can offer some interpretability. Here I showed an example in the face detection task. We can see that the kernels in this face detection task shows different levels of pattern. So in a similar fashion, for a given molecule, we can also look at a molecular neighborhood and convolve this with a molecular kernel. What we want from this molecular convolution is a similarity score. There are several properties we want from this similarity score. First of all, the more similar a molecular neighborhood is to the molecular kernel, and we want the score also to be higher. And secondly, we also want this molecular convolution to be rotation invariant. And finally, we can see that these molecular kernels can also offer the benefit of interpretability. So how do we actually calculate this similarity score? So this similarity score is made from 3 subscores, and the final similarity score is the weighted average of these subscores. And also, we note that if the degree in the neighborhood does not agree with the degree in the kernel, then this similarity score will be set to 0. Now let's look at these subscores. First, for the center subscore, so we compare the similarity of the center node in both the neighborhood and the kernel. Secondly, for the neighbor subscore, we first align the neighbors and compares the similarity of the neighbors. But you may wonder, if this is the best alignment? Well, there could be different ways of aligning them. So we find the best alignment, which gives the highest subscore. And then we can use the same best alignment to also calculate the similarities between edges. So once we have the similarity score, then we can go back and look at the problem we were facing earlier, how to distinguish the chiral molecules. The idea here is to compare the orientation of a certain molecule to a reference. If the orientation is the same as the reference, then we can set the indicator to 1. Otherwise, we set the indicator to -1. And the similarity score can be updated by multiplying with this indicator. Specifically, how do we calculate this orientation? We use signed tetrahedral volume. So basically, first, we construct the 3 vectors ABC from arbitrarily 4 neighbors. And then we can calculate the signed tetrahedral volume by doing 1/6 times A, then cross product B and dot product C. As you might notice, this volume can be both positive or negative, which indicates its orientation. And we can then compare the sign of this neighborhood to the kernel. If the sign is the same as the kernel, then it is of the same orientation. Otherwise, it is of a different orientation. This way, we can distinguish the chiral molecule. So, with all these, we can look at the overview of our model. Our model is named Molecular Kernel Graph Neural Network, or MolKGNN. So basically, for the given n-atom molecule, if we look at its molecular neighborhood and convolve this with a set of learnable kernels, we can construct our message from the similarity scores. Then we can aggregate the message and update the atom attributes using those aggregated messages, then move on to the next layer. So here, we're going to show how we evaluate our method. First, let's look at the data set. So there are several commonly used benchmarking data sets in the GNN community. However, they are not very suitable for evaluating our work. For example, some data sets, they only have limited number of data. Secondly, some data sets, they do not have processing to remove experimental artifacts so that it may contain very high false positive rate. And finally, the dataset may not be relevant to molecular activity. So here I propose to use a different dataset which originate from the PubChem dataset. And those datasets are identified by the PubChem AID as shown here. And the reason for choosing this dataset can be seen as follows. First, it has at least 150 confirmed active compounds, so it's a well-curated dataset. Secondly, it has a diverse target classes. And finally, it's also realistic because it has a large number of compounds and also a very imbalanced label. And besides that, we also use the domain-relevant metric to evaluate our model. So in a realistic drug discovery campaign, only the top-ranked predictions will be experimentally validated, and those predicted inactive molecules, they are not going to be validated because it's too expensive. So we want to use the ranged log AUC to capture this. So the range log AUC is used to bias towards the performance of the model for these top-ranked predictions. So basically, we only integrate over the small range of the false positive rate. Those small positive rate, they correspond to the high threshold in the predictive value. And specifically, we follow previous papers by choosing the range to be 0.001 to 0.1. So for the perfect classifier, this range log AUC will get a value of 1. And for a random classifier, this metric will get a value approximately to 0.02. So now let's look at the result. So here we've shown 3 sets of different models for our benchmark. So the first set is 3D GNN, and it contains SHANet, SphereNet, and DynNet++. The second one is chirality sensitive models, which can also capture the chirality, and we choose this model, Chiral. And finally, we also have another set that shows the similar architecture as ours, and we have a model MolKGNN here. So as you can see from the results, so our model has a superior performance and also has the lowest average rank among all these models. So in addition to this domain relevant metric, we also evaluated our model using a generic metric, AUC. As you can see here, our model still performs on par with other models. And also here, we can also see that this general metric, the result is not necessarily aligned with the domain relevant metric. So this just highlights the fact that the domain relevant metric is more useful in this specific scenario and highlights the practical value of our model. And finally, we'd like to show our interpretability result. Here on the left is a translated learned kernel. And this, on the right, we also show 3 examples from the training set that shows this pattern. And this shows our model's interpretability, and also providing an example of the learned kernel also aligns with the domain knowledge, because this learned kernel is also an important substructure known in the medicinal chemistry as a trifluoromethanol group. And in conclusion, here in this work, we proposed a new framework named the MolKGNN that has a completely new convolution operation. And secondly, we also use a better chirality characterization. And finally, we use a more realistic dataset and the metric to evaluate our work. With that, I'd like to thank my advisors and my founding agents for the support. Specifically, I'd like to thank AAAI Student Scholarship and Volunteer Program, and also NVIDIA Academic Hardware Grant Program for the support. And I would also like to thank you all for your attention, and I'm happy to take any questions.